over everything on the right-hand side, so we'll say partial t, the integral of control volume, rho velocity over the control volume is equal to my control surface integral of my momentum minus the integral of my pressure ds and plus my external force. And there you have it. So if it's steady state, what happens to that term? 0. So this term, 0, steady state. Now it's an assumption that we're going to keep doing quite a bit, so we're going to say SS. So we understand what SS refers to. So this is equal to 0. So what do I have? I have my pressure forces that are applying to the surface of the engine in general, my external force, which is your drag force on the engine, and this is your what you're trying to do is thrust. And when you're saying integral over a control surface, think of the people that are coming into the room versus what's going out. We just outlined that same example again in terms of momentum, right? There's the door, there's a door, and there's another door.
Shouldn't that be a negative?
If I somehow bring in, people are running, two people are running right here. You see it, okay. And two people are running right here at a velocity of, let's say, 10 miles per hour. They're all running at 10 miles per hour. Somehow, magically, in the room, I give them coffee, and they double their speed. Okay? They're going to go all 4 of them out, right? And double their speed at 20 miles per hour. Well, take a look at the relative change associated with this. Obviously, they're not going to use a sufficient amount of force to drive the room with thrust. But this is this time. I'm looking at the balance of the momentum across. Making sense? Question?
I believe that term should be negative.
Which term?
Yeah.
First term on the right, first term.
The control
yes.
surface.
They moved it on the other side. Doesn't matter. Very good question. Doesn't matter. As long as I know my inputs and outputs, which is relative to the right force, I'm good. Okay? So, let's say, for example, so here, what is the integral going to be like? It's going to be what comes out versus what goes in. By putting that minus sign, it's going to be in minus out. Okay? So you could, as long as you know your reference frame relative to your forces, you're okay in terms of sign wise. But yes, absolutely, from the algebra standpoint, you're correct. This is minus. But now you know that the integral has to be the outcome.
That's what I was thinking, because
we're going to be doing that. We're assuming no chemical changes right now. Yeah, but you're going to be doing, well, we just said coffee. That's sort of a chemical change, right? So yes, we have to, that's how you get propulsion. That's why combustion is the main dominant sort of mechanism for inducing a significant amount of thrust, because it is where you can get that significant coffee that can run fast. Okay? But we'll get into the chemical. We're going to do ideal mixtures, gas mixtures first, and then we're going to go reacting mixtures, which is going to cover how can we get these people to run double their speed. Okay? All right, any questions on this? Let's do a quick example. So, if we assume, this equation obviously is your conservation, your general form of conservation of momentum. So let me highlight it here. Let me write it here and say this is your conservation of momentum in a general form, and it has the unsteady term. But you understand, if I assume steady state, I'm going to take this equal to 0. So what is our general form that we're gonna be generally working with in this semester? So if we assume 1D flow, okay, for based on this equation right here, well, that's going to be the sum of inlets, m dot inlet multiplied by velocity of inlet, sum of outlet, m dot outlet multiplied by the velocity of outlet minus P N ES plus F external is equal to 0. So you notice the minus sign where it went about? When you're doing an integral, it's out minus in, and I just multiplied it automatically. So you just get used to it at some point, just know the coordinate system. But yes, we need to be careful with our sign, which force is applying to what. Make sense? And think of it this way. This is a drag force. So you know it's going in the wrong direction of where the thrust is, right? So where's your thrust coming from? It's right here. So from there you can determine quite a bit actually. People get the signs incorrect because they lose where the forces are coming about. But I know my drag force is going to be opposing to my thrust. My thrust wants to drive me forward, drag force is opposing to it. So this has to be opposite to this, and my inlet has to be opposite to my outlet. It's not going to be in the same direction, otherwise we're shooting out thrust in both areas, right? So that's not going to happen. And this is a pressure term throughout the whole engine altogether. We'll do an example right now. So consider an engine held in place by a support so I have some engine of some sort, this, and it's held by a support to some aircraft of some sort. So let me apply my control volume right here. And primarily what I have is some flow that's coming in right here at this. You're gonna actually do example, or you're gonna do one of the problems in the homework exactly like this. So inlet conditions, and I got some thrusters being produced right here. U exit, A exit, E exit, and exit. And I have some total area like this. And this engine is not going to run out of just producing thrust out of air. I have to introduce some m dot fuel. So coming out from the control volume right here, I'm introducing m dot fuel. So that's a mass that's coming into the system. And that's my system overall. Velocity outside the engine, let's assume it's a relative velocity. So right here, anywhere around, the velocity is equal to 0, and P is equal to P atmospheric. And this is equal to about here. Okay, so let's apply our conservation of mass. Well, for this, I got an m dot in, I got an m dot fuel is equal to m dot exit. So very straightforward. Conservation of mass, m dot in plus m dot fuel going to my system is equal to my m dot exit. That's our conservation of mass. What did I assume by doing this, by the way? Very good, steady state. So think of this equation again. This equation right here. This right here, steady state, sum of masses that are going in minus what goes out. Well, let's move the out on the other side and just change the minus, okay? You're relating the picture. Okay, conservation of momentum. Let's see. We just wrote this equation up here, so let's try to do this equation. So sum of masses that are going in, so m dot I ui plus m dot fuel. What is the velocity of that fuel relative to my x direction?
0.
You guys are good. All right, so I should skip conservation of energy then. That would be great. Somebody said that would be great. Okay. All right, what goes out? Plus my sum of pressure forces that I have applying on my surface. So what do I have? I have this pressure relative to this, so it will be EI multiplied by AI plus atmospheric pressure multiplied by the area difference, which is only in the one-dimensional direction. It will be A, which is total area, minus A of the inlet, which is right here, minus, so it's an integral form. Yeah, it's outlet minus inlet, so we already incorporated the sign. So what you're getting is exit, P exit multiplied by area exit. Now I need to get the other side as well from the downstream side, minus P atmospheric, A minus A exit. What am I missing there? One force right here, F external. So plus what? F external, which is my drag force, equals to 0. My drag force, or if it's a rocket, like the gravitational force of the weight. So it will be pointing downwards. I'm trying to launch that rocket vertically. So it's the same principle. Or if it's at an angle, then you decompose your weight forces and figure out how much is this way versus how much is going down. Same equation is right here. This term is right here. These are the sum of inlets. This is the sum of exits. The integral of the pressure, now it's a minus sign, so we have to do outlet minus inlet, but then it's a minus, so I switch things right away. I did inlet minus outlet. So inlet, I have pressure forces applied to right here, but then I have pressure forces that are being applied right there, relative to my pressure forces that are here. It's still atmospheric. And the area exit, is different than the area inlet. Now, why is that important for me? Because I'm going to tailor that CE nozzle or configurations in downstream to change my thruster. So you're going to be balancing these areas and controlling the engine accordingly. F exit, well, that you don't really control because it depends on the vehicle you're ready to sell. So from there, my final equation will look like mi ui, simplifying things, mi plus m dot fuel u exit plus pi minus p atmospheric, ai minus e exit minus p atmospheric, a exit plus f exit is equal to 0, and that is your final equation. All right, question?
M dot E.
M dot E. Oh, very good question. Where did I switch it? Why did I switch it? No?
You have M dot FUE in the top.
So somebody said conservation of mass. Do you see where it came from? I'm not going to throw that equation at the top. Now, why is that important? Because I need to know the exit, and I already have an equation right here, so simplify your things and substitute it in there.
Yeah.
And we're going to do that quite a bit.
Yeah, okay.
Okay, makes sense? So I'll highlight it in red. So, there you go. All right, any questions thus far? Jumped into energy equation? No question.
Why did you multiply the mass flow rate of the fuel times 0?
Okay, very good question. Somebody else, can they answer why did we multiply by 0? That, but not necessarily.
It's going forces in direction.
It's going in the vertical direction. Does it have a U component? No, it has a V component, and I said I'm going to focus on the one-dimensional approximation. Now, you're absolutely correct. You want to take that into consideration. Get your masters. Yes, so we're going to go over mostly one-dimensional based systems, and if you go for grad school, you're going to take the same one-dimensional equations and start applying it to the two-dimensional and three-dimensional. So, but it's the same exact equations that you already know, you just have to account for it. So you already know that there's a V component. So if I want to count for all V components in there, what's going to happen is this is going to get in, and it's actually going to turn inwards. It's a very, very small component that I could just neglect. But very good question. All right, any further questions? Jump into the energy.
Spring.
All right. Now the energy is a bit complicated just because it's one equation, but it has a lot of, it's not just the first law, right? If you take it based on the first law, it's easy. But actually the momentum should be the hardest, which we just went through. But there's more components to the energy, meaning you have the first law, and you have entropy to deal with. You can't just go backwards, and I'm going to highlight those. So let's first introduce first law and use the first law, which is straightforward, but then there is certain limitations of how you use the first law, and that's why you have to account for all of those, which just primarily comes through the entropy. So conservation of energy. We said it's the first law of thermal. Oh, sorry. They have multiple marks here, so I don't know. Right. Okay. So conservation of law, or conservation of energy, sorry, is total energy is equal to internal energy plus kinetic energy plus my potential energy. So total energy internal energy and kinetic energy and potential. For a closed system, the total energy is equal to Q net in plus W net in or out, depending on, or summation. So the general form in a rate version, actually let's not make it N, let's just make it summation. In a rate version, well, it's D total energy rate of change is equal to the sum of Q net rate plus W net rate. Nothing new, it's rate of change of the energy of the system is equal to what goes in and out. There's a heat and work. We'll do a little bit of examples on that. Now, we said also specific energy, which total energy is equal to the interval of density, lowercase energy over some volume. So internal energy is equal to